So the fact that all riskless assets must earn the same return is by now hopefully a not very controversial statement, but we'll see that it's a very important statement in the sense that it has a lot of applications. So let's look at one particular application of that, which is about kind of like deciding what's an optimal time to cut down trees in a forest, right? So this is basically when we say forest, we mean kind of like a small sort of commercial forest where the trees have been grown in order to kind of generate wood for commercial use. And there you have got basically the size of a forest, which is measured in terms of the wood that one can get from it, is some function of time t. Okay, so this function is ft that is given to us. And we know that the price of the wood that we can get is also constant and it's normalized to 1 for this example. And initially the rate of the growth of the trees are high, but over time they kind of like reduce, and that is what the situation is. So the question that we are interested in thinking is that if there was indeed a perfect market, in that case, when should that forest be cut, right? So the answer, interestingly, is that the forest should be cut when the rate of the growth of the forest equals the interest rate. Okay. Now, intuitively, why is that the case? Because before that, the forest is earning a higher rate of return than the money in the bank. And after the point where the growth rate of the forest equals the interest rate, the growth rate of the forest keeps declining. And so at that point, the forest starts earning less than the money in the bank, right? So the optimal time is actually to just cut it when the two growth rates are actually equal to the interest rate. So let's take a example to kind of like clarify some of these ideas. So suppose that you know that the value of the forest changes with time according to the following function. Vt is equal to minus 1000 plus 1000t minus 10t square, right? So this is basically a quadratic function if you kind of like recognize it. And the function is basically maximized at a value t, which is given by the derivative of this v at that value should be equal to 0, right? So basically, how do you maximize this vt? Figure out where v prime t is equal to 0 and solve for t, right? So if you take the derivative here, you are going to get 1000 minus 20t, and then if you set that equal to 0, you end up getting t equal to 50. So if you were just kind of like thinking very simplistically, one answer would have been, if I want to maximize the amount of money that I'm getting from this forest, I should look at where this value of the forest is maximized, and I should choose that point, right? So here our calculations would indicate t equal to 50. However, there is a basic kind of like mistake that is being made here, in the sense that it ignores what are the outside options that are available to somebody who actually cuts down the forest, gets the money that is there, and then has the option of putting the money in the bank, right? So before we get into that calculation, let's think about how to think about the rate of return in this scenario, because this is slightly different compared to what we have been discussing so far. So far we have been discussing about time in a discrete time period where you've got t equal to 0, 1, and so on. When you've got time in continuous period, then the definition of the rate of return becomes the following: v prime t by vt. Now, if you notice carefully, this is actually very similar to the expression that we have got for the discrete time. So because the numerator is the change in the value of t, in the discrete time, remember, we used to have this c1 minus c0, right, divided by c0. So that is actually very similar to what we have here, right? Except this is the continuous version. So because in continuous time, there's no t and t plus 1, right? Each moment the value is changing. So we have to take the limit and so on. Okay. So what do we get from here? So therefore, we now have that we have already got the expression for vt that is given to us. So we can just put that in. And we also have an expression for v prime t, which we can put in. So this v prime t by vt is given by this, right? And recall that we also actually are suppose that the interest rate is given to us at 10%. So one question is, when should the asset be sold? The answer here is that when the rate of return to holding the asset falls to 10%. Okay. So it means that what you want to do is that you want to wait till the rate of return of this forest is falling to 10%. At that point, you want to kind of like cut down the tree and kind of sell the wood, and then put the money that you get from selling the wood in the bank and keep earning a 10% rate of return from interest, which is going to be more than what you would have been earning if you had just kept the forest as it is, right? So we can solve for this 10%. So we say that the rate of return of this asset, which remember is this expression that we saw here, and which we have for this particular functional form that we had, this becomes this. So we want to wait till this reaches 0.1 and at that point sell it, right? So you can kind of like solve it, and then you end up getting t equal to 10. Let's just give a basic argument about why this is a good idea than waiting for time t equal to 50 and then kind of like cutting down the forest, right? So at t equal to 10, what's the value of the asset? Well, we can just plug it in here, t equal to 10, and see. So if you cut it down at t equal to 10, you are going to get basically 8,000 units of money at t equal to 10, right? And now if you put this money in the bank at an interest rate of 10% for 40 years, then this amount of money in 50 years from now is going to become 8,000 multiplied by 1.1 to the power 40, right? So that's approximately equal to 362,074. Okay. And now if you compare this with the amount of money that you would have got at t equal to 50, if you had waited till t equal to 50 to cut down the forest. So you can put in t equal to 50 here, and you will see that that's equal to 24,000, right? So this is an amount of money which is significantly larger than this amount of money, right? So what you get from here is that the idea that if you want to have the largest amount of money at some unspecified point in the future, then basically you should invest your money in the asset with the highest return possible that at that point, right? Of course, this assumes quite a lot of like implicit assumptions, right? That there are no transaction costs, that there are like all the returns are known and so on, right? Under this assumption, you have this lesson that is true, right? However, one thing that we didn't prove, but we used here, is this result that you're going to actually kind of like wait till you reach this v prime t by vt to be equal to 0.1, right? But why is that the case, right? Why, how do we know that that is true? That is exactly the point where things are maximized. So in order to kind of like analyze that, we have to go back and do a bit more preparatory work, right? So far what we have been discussing is basically a case where compounding happens at discrete points in time. What we want to now first do is to figure out an expression for what happens when compounding happens continuously, right? So let's just take a small detour, understand that, and then come back to this question. So how do we kind of do it? Well, basically what we are going to do is we are going to take more and more frequent payments and compounding that is going to be done, and then think about what is the implication of taking the limit. So suppose that you have got, you're investing 1 unit of money in an asset that is going to pay an interest rate of R when the interest is paid once a year, right? So what is this amount of money that's going to become? So after t years, this is going to be translating into 1 plus R to the power t units of money, right? This is the future value of money concept that we have discussed. Now, this is interest being paid out once a year, right? But now suppose that instead of interest being paid out every year, suppose that interest is now being paid out every month, and that the monthly interest rate is nothing but the interest rate that you had R, but divided by 12, right? So every month, this is the amount that is going to be paid out in interest, and then you can kind of like add this to the principal, and then again, you get an interest on this new principal plus interest, right? So what is that going to mean? So that means that if you are thinking in terms of t years, so then there's going to be 12 times t number of payments, right? So for example, if you were thinking of 2 years, then that will mean that because you have got monthly payments, they are now going to be total of 24 payments. And as a result of that, after t years, you're going to have this much amount of money, right? So each time you're getting 1 plus r by 12, and this is being compounded 12t times. And so therefore you end up getting this expression, which is 1 plus r by 12 to the power 12 t. Okay. Now, if the interest rate is going to be paid daily, this means that you are going to actually can do the same calculation. So instead of r by 12, you are going to have r by 365. And then the total amount of payments is going to be 365 times t, assuming each year has 365 days. And so therefore, now the amount of money that you are going to have at the end of t years is given by 1 plus r by 365 to the power 365t, right? So there's no reason to stop at daily. Why don't we kind of like think about, suppose the interest is paid n times, where this can be n equal to 1 for annual payments, n equal to 12 for monthly, n equal to 365 for daily, n equal to, you can think of 365 into 2 for twice daily, and so on. So suppose it's more general and that it is going to pay it n times. So we can do the same calculation as we did. And this expression will now, instead of 1 plus r by 12 or 1 plus r by 365, because it's being paid n times, you're going to have 1 plus r by n. And the total number of payments that will happen in t years is given by n multiplied by t, right? So you're raising this to the power. Okay. So now, question is, how much money would one have if the interest rate is being paid continuously, so every moment, right? So this is the same as figuring out what's the actually the limit of this expression with regards to n going to infinity. And if you look at the limit of n to going to infinity of this 1 by 1 plus r by n to the power n by t, so this is nothing but actually e to the power rt, right? So this is actually the definition of e to the power x that you might have seen in your high school algebra, right? So this is the answer, that if interest is being compounded at every point in time, then 1 unit of money in t years is going to become e to the power rt. And you can see that this is the discrete, the equivalent that you have seen, the future value of money that you have shown. But if this becomes the same as e to the power rt when compounding is happening at every moment in time. Okay, now that we have this kind of like detour and this expression, let's come back to this problem of when to cut down the tree, right? So how did this detour help us? So now we are going to frame this in a continuous time, and we are going to think about where compounding is going to happen at each point in time. So the forest is going to be worth, let us say, ft at time t. Now, from present value perspective, this is the same as saying that the value of the forest today's perspective, if we cut it down at time period t, is going to be ft divided by e to the power rt. Now, why do we have e to the power rt? So imagine that if this was discrete time, what you would have required in order to calculate present value is you would have needed to divide by 1 plus r to the power t, right? Now, the equivalent of this 1 plus r to the power t in continuous time is this e to the power rt when you have got thing happening, the compounding happening continuously. So therefore, this is the value of the forest if it is harvested at time t. So that's e to the power minus rt multiplied by f of t. Now, if you want to maximize this present value, one way is that you go about differentiating this with respect to time, and then you set it equal to 0, and then you solve for the time, right? So if you differentiate this, this is you can apply the product rule. And so v prime t is e to the power minus rt f prime t minus r into e to the power minus rt ft equal to 0, right? So you can cancel out the e to the power minus rt's. And now if you rearrange, you end up getting that r is equal to f prime t by ft, right? So this actually verifies our claim that the optimal time t in which we should have actually cut the forest satisfies the condition that basically the rate of interest, which is r, has to equal the rate of growth of the value of the forest, which is given by this f prime t by ft. So hence this actually proves what we had claimed before when we were doing this exercise in the example of like when should we actually optimally decide to cut down the forest.